So what we're going to do with the other 4 or 5 minutes class, we have 2 other sections to teach before the end of the week. So let's get started. So I'm going to leave this up as I hunt down where the next set of notes are. 2.6. Oh, man. All right. Nope, not what I wanted. Where's what I want? Oh, here's the next set of answers. Perfect. Now we just need the next set of notes. All right. Someone's house is on fire. Got 45 minutes. See how far do you think I can make it all the way through? I assure you I could teach all these notes in like 20 minutes, but none of it. The understanding level might not be there. Let's just get to 5. If we get to 5, I'll be happy, right? All right. I love my calculus classes. Like, are you going to teach this fast every time? I was like, yeah, because you have 2 options, right? I can either not teach you parts of the book and still test you on it, or I can just teach slightly fast and then you can watch. You can just watch the lectures on YouTube and slow it down then. And I was like, let's do the latter. Okay, I had a feeling. Have you guys ever been in math class? Well, I expect you to know everything out of the book, and so lectures will not be all inclusive. I'm like, yeah, that's not good for a math class. You guys had that before? All of a sudden you get to a test like, where did this come from? Had it in physics. Oh, dude, physics was the worst. There's stuff I remember doing stuff in physics like we didn't need anything close about what this looked like. Oh man, it was a rough. I took physics here at UNLV. I guess I'll tell the story because this will get cut out and you won't hear it on the videos. I took it here at UNLV, and all my classes I took were, they're all graded on a curve, which is like, oh, that's great, right? No, one of the teachers, who is unfortunately no longer with us, really nice guy, but kind of a strange, says, I don't believe in inflation of grades. C should mean average. And so he took his grades, drew the middle line, and he failed half his students. To take his class twice. It's just like, well, I had to be in that class and fail. Great. Oh man. Anyways, and then I was in this modern physics class where they teach you quantum mechanics and all this other stuff, and you know, it seems like, oh, I found this really cool way of doing homework. It's like, you can't do it that way. Then it took me 5 seconds to dawn on it. If everything's graded on a curve, they were purposely sabotaging other people's grades. Oh man, this is terrible. Oh man, I still have one of my friends in there. He was hilarious. He ended up working on rocketry, right? And he's I don't remember where he went. He doesn't work for SpaceX, but he went somewhere, and I kept in contact for a while. I mean, he got married, and he used to do stuff that would just drive his wife insane. He's like, why didn't you empty the dishwasher? And he go, it doesn't take a rocket scientist to empty a dishwasher. I'm like, dude, keep that up. You're not going to be married long. Anyways, let's talk about math now. We got it already. Oh. Anyways, so let's talk about systems of equation and Gaussian elimination. So your quiz this week will be how to solve one of these by hand. So let's go through it. I'm going to teach you how to do this by hand. I'm going to teach you how to do this in calculator for any size of system of equations. You guys will probably exclusively only use the calculator from now on, but we'll do it by hand for a second. So let's talk about what does it mean to be a system of equations. So a system of equations has this little bracket right here. That means these 2 equations occur simultaneously, right? And that means both of these And a solution must satisfy all equations. And what I mean by satisfy, makes them true. So is this a solution? So just to test if something is a solution, we're going to just type in everywhere I see an x, I'm going to put in -2. And when I plug in variables into an equation, I always put it in parentheses to make sure that I respect the negative correctly. And that like if I square the negative, because there's this, -4 squared is not equal to minus the quantity of -4 squared. Minus the squared this is not equal. And so that's why I always plug it in. So you always respect the substitution. All right. So if I plug through this, I indeed get -3. So this one's correct. But not only does this one have to be correct, this one has to be correct. So I have -2 times -2, which is +4. And then I have 2. Oops, that doesn't go in that. 2 times the 3. And that gives me 10. And so here, in order to be a solution, it must satisfy. These look like checking marks. So this one works and this one works. Okay, so here, that's what it means to be a solution. It satisfies all of them. So you probably learned a couple different methods, maybe. I come to find out sometimes you guys don't know how to solve any system of equations, and I cry a little on the inside. But we'll get through it. So one of the common, what you mostly tend to do for nonlinears, this is what you have to do. Elimination doesn't work that well. I mean, it can. It's substitution. You solve one equation for one of the variables. You take what you got and you stuff it back in. So you substitute back into the other equation to get a value. And then once you get a value for that one, you go back to the first one, get back the other value, called back substitution. So that's what you've done before. The other way you've done it is you've added some multiple of one to another to eliminate one of the variables, added them up, and then you have an equation, one variable, figure out what that is, and then go back. So those are the two things you probably have done. So let's do them, right? So you can remember how to do them. And then we'll look at some different other ways of solving this. And then we'll get into the numerical way, which is the more important way. All right, so here, if I was going to solve this one, I will do, let's do elimination on this one and substitution on this one, because elimination on this one doesn't work too well, but it works well. So here, notice here I have this one, I have a -y and a +2y. So I'm going to multiply this whole equation by 2. So I'm going to take this, so this will be 3x plus 2y equals 14. And then I'm going to take, so equation 1 and then equation 2. So this is equation 1, I'm going to put 2 times equation 2. So 2 times equation 2 is going to equal 2x minus 2y equals 4. And then what you do is at this point, you add them up. Have you guys seen this before? Or you've done this before? See most people nodding their head yes. Okay. If not, I may slow down a little bit just not to lose. But if most people have seen it before, we'll just go ahead. So here I'll get 5x. Here I'll get 0 by design. So 5x is equal to 18. So what is x equal? Well, x equals this awful number, 18/5. Well, yay, right? Then I can just plug this back into 2. So I'm going to go back to equation 2. I know what this is. This is 18/5. I'm going to minus out a y, and I'm going to get 2. If I solve for that, you guys seen this symbol before? This one, where the equals plus the arrow means implies. It means, instead of writing, it means this implies that y is equal to 8/5. It's just a nice way of saying, instead of writing it on the next row, because usually when you do math, you'll like do a line, do a line, do a line. If you do a line and you don't want to write it on the next line, just write implies the next line. That's what it means. What you're secretly doing here is you're always saying this implies this, which implies this, which implies this, and that's how you're doing your math. But if you do it on the same line, you tend to write the imply. All these tend to be assumed when you don't. When you're doing formal math proofs, you'll do this implies this implies this. That's how you write them. Now, even in then, you don't always write the explicit implies. I'm on the wrong layer. That's good to know. So here we have our solution. Our solution to this, hold on, let me write out my solution very clearly. It's 18/5, 8/5. Did I do that right? Yeah. And so here's here's our solution. Remember, our solution is an ordered pair. It's two things. You can write out, or you can box both of this. If you box this, that'd be also okay, because then you have what x is and what y equals. All right, so the other method is substitution. So I'm going to take equation 1 here. I'm going to solve it for y. So y equals 1 minus 2x. I'm going to plug that into equation 2. So this is going to be 3x plus 4. I know what y is. It's 1 minus 2x equals to 14. Now that I know that, I can simplify. So this will be x plus 4 minus 8x equals 14. So I have minus 5x is equal to 10. That means that implies x is equal to minus 2. And then once I can just plug that back into 1. So 1 is 1 minus a minus, or oops, hold on, minus 2 times a minus 2. So that gives me 3. No, that gives me 5. I can do math. 1 minus 4, or 1 minus a negative 4 would be positive 4, gives you 5. And so my solution here is minus 2 and 5. Okay. So this was elimination, and this was substitution. So you've probably done it for a 2x2 system. Have you guys done it for a 3x3 system? Yes, some people yes, some people no. Some people don't remember. All right, so let's do it for. All right, so if we're going to do this graphically, we're going to graph all the lines, right? And then it's just the intersection. So here for the 2x2 systems, we can have exactly one solution, no solution, infinite solution. This is actually just easiest seen graphically. So here, if I have my first equation, so if I equation 1 and then equation 2, this will be my answer. Just wherever the intersection is, this is my answer. But you can also have it where the lines do not intersect, right? So here's to make this equation 1. This will be my equation 2. And since they are parallel, just assume that these are parallel, right? These will never intersect, so there's no solution. Or if I have equation 1, and then here in red, it's also equation 2. We have infinitely many solutions. And an example of this would be if I had y minus, or if I had x minus y equal to 0, then 2x minus 2y equal to 0. If this is my system, all I need is x equal to y. Anything that's on the x equal y line works, right? And so this has an infinite number of solutions. All right, so let's get into a 3x3 system. Let's get into a 3x3 because once if you can do a 2x2, you're doing good. If you can do a 3x3, if you can really know how to do a 3x3, you can really do an n by n, right? And infinite. I could give you any finite amount of values, variables with that exact finite amount of equations, and you should be able to produce a solution. So on the exam, we're going to do 10 by 10 and watch your brains ooze out. Actually, if you're allowed to use a calculator, who cares, right? You just type it into the big beast and be done with it. Let's go through this. If I wanted to solve this, what would I do? What would I do to solve this? Do you know what at least one of the variables is? Sure, right?
Just
you know
plug.
Yeah. Go for it. Go for it. Someone almost said it.
Yeah, just plug z into it. You'll get y equals -1. And you could plug everything into the top equation.
Yeah, that's it.
Find out that x equals 0.
Perfect. And so here, when we do this, that'll be exactly it. So here we plug this in. So we have z equals to 3. So I know what the first part of my solution is, right? It's 3. So here, I'm going to plug 3 into here. So I plug 3 into here. So I have y plus 2 times 3 is equal to 5. That means y equals -2. Oops, no, -1. I can do math. This is V6, move it over, -1. So we have -1. So now I have that. So I have x minus 2 times a -1 minus 3 equals 1. So here I'll have +2, -3, and I want x equal to 1. So x in this case was 2. And then we get our solution. Okay, so once we get, so if I give you anything in this form, you just back substitute, get a solution, then you have 2 solutions. You're going to back substitute in this one, get that solution. So given anything, we're going to try to get it into this form. And so here are some operations we can do that give equivalent system. These operations do not change the solution of the system. And I'm going to explain this since we have time exactly why. If I wrote, I'm going to write notes here that which I will erase later. So I'm going to write explaining notes here, but I only need, let's see if I can help you guys when you type notes. I only need this much space to solve the problem. I know that already because I've done it before. So here, let's just look at, let's look at this one. If I'm going to interchange one equation for another. So if I took this and I call this equation 1, this equation 2, and this equation 3, if I wrote this system here as x plus 2y minus z equals 13, x minus 2y plus 3z equals 1, 3x plus 2y minus 5z equal 3. If I changed the answer to this in any way, the answer is no, right? Because if x, y, and z worked for equation 2 before, it's going to work for equation the now equation 1, right? It's the same equation, right? So interchanging will have no effect on the solution. I'm just moving stuff around. I could easily call this equation alpha, this one equation moose, and equation Captain America, right? For who I care, right? It doesn't matter what I name them or how I label them, how I deal with them, right? I could do whatever I want. And so interchanging one equation for another doesn't matter. If I multiply one equation by a non-zero constant, that's fine, right? If I take this whole thing again, and here, let's just say if we take this, and I'm going to have x plus 2y minus z equals 13. And then I'm going to say this is 2x minus 4y minus 6z equals 2. And I take 3x plus 2y minus 5z is equal to 3. So all I've done is taken this equation and multiplied by 2. Have I changed any of my solutions before? No. This should have zero effect on the solutions, right? Because here, if the correct answer x, y, and z satisfy this equation, it will also satisfy this equation. The only one that's kind of weird is I can add a non-multiple zero from one equation to another. And see if I can explain this one So I'm going to take equation 1. I'm going to take x minus 2y plus 3z. So I'm taking the equation 1 from this side. And that's equal to 1. And then I'm going to add 13 to both sides. Can I do that? Can I add 13 to both sides?
Why not?
Sure, why not, right? But what do I know what 13 is? Is 13 also equal to this? Yeah, that's what that equation says. That's 13. And so instead of writing 13 here, I'm going to write x plus 2y minus z. So if I add this to this side and add this to this side, have I changed the equation at all? No. So what would have solved this will also still solve the new one. And so this is the only one that's kind of weird. So I can add multiples. So if I added, instead of 13, I put in, oops, of course I was on the wrong layer. I'll just go back. I could have added 26. And I can add 26 to both sides. Well, in this case, I have to add 2x plus 4y minus 2z, right? Because that's 2 times this, right? To both sides. And I still get the same thing. So this is the one that's a little harder to understand why it works, but it's perfectly fine. All right, so now we've done all this, but what have I done here? I made what they call upper division math alphabet soup. You just move stuff around. You haven't done anything useful, right? So let's do useful things, right? Let's do useful things. So here, if I label all this, my useful thing is I'm going to take this. I want to get rid of this right here, right? And I want to get rid of this right here. And so what am I going to do? I'm going to take equation. So I'm going to rewrite this equation. And I have x minus 2y plus 3z equals to 1. And then I'm going to take, instead of equation 2, I'm going to take equation 2 and I'm going to add to it a negative 1 times equation 1. Now, can I do that? Sure, right? I'm allowed to add a non-multiple zero of one equation to another because of this logic, right? If I add 26 to one side, I can add 26 to the other side. And so since these are truly equal, if I add a negative of this to one side, I can add a negative of this to the other side. But why would I do such things? Well, obviously, if I add negative of this to this, I'm going to get 0x, right? And so I just have nothing here. Negative of 2y added to 2y would be 4y. Negative of 3z added to negative z would be minus 4z. And a negative 1 added to this will give me 12. Okay, so I've done that. I can do that. And in fact, I can do this again. I can take equation 3 and I can add to it minus 3 times equation 1, right? So I'm going to take this equation and add negative 3 of the first one. So negative 3 to this will give me 0 again. Minus 3 here would give me 8. So 2 minus a negative 6 will give me 8. And then negative 5 minus 15. Yes. Hold on. Minus 20. Am I doing this right? All of a sudden, my notes are not complete, and I'm worried about it. Hold on. I'm pretty sure I have the answer in 2 seconds. No, I never finished this one. No, I'm just full of crazy. Yada, yada, yada. All right. And that would equal 3 minus 3 of negative 1 would be 0, right? Does everyone see what I did here?
I think it should be negative 14z for that last equation.
You're probably right. 3 times, oh, yeah, because I can't do math. Thank you. So this is minus 5 minus 9 would be minus 14. Equals to 0. Yes. Okay. So let's make our lives easier and let's solve this. So here I'm going to rewrite the same first equation. This equation, I'm going to divide it by 4. So here I'm going to take equation 2 and I'm going to multiply it by a fourth. Now, why would I do such a crazy thing? Well, if I divide out 4, I'll have y minus z equals 3. And then 8y minus 14z equals 0. All right, now I'm going to take this equation. I'm going to leave it the same. And then I'm going to take this one and I'm going to minus, so I'm going to take equation 3 and minus out 8 of equation 2. Now, why would I do that? I get rid of the y. And so if I minus out 8 of equation 2, I get nothing. So I'll have nothing here, nothing here. So I'll have minus 14, hold on, minus 14z minus negative 8, so that'd be plus 8, so that'll give me, I can do math, 6z, right? And then minus 8 here, minus 8 here, so negative 8 times 3 would give me, hold on, minus 24. And so that means z is equal to minus 4. And if z is equal to minus 4, y is equal to, I can do this in my head, I swear. I don't have to, but this will be minus, so y plus 4, so move the 4 over, so y is equal to minus 1. And then if that's true, I have 2. I have minus 12, so I have positive, so I have negative 10. X equals to 11. I don't think that's right. Hold on. Let me see what I did wrong. All of a sudden, I don't think I did my mental math right. This is why you never ever do this by hand. I'm sure I have to type this in Wolfram Alpha so I can figure out what I did wrong. I want to do a system of equations. System of equations. It'll produce a little cheat sheet for you, and you just type it in. So let's go back to the original. Always type in the original. Yeah. I remember how I said at the beginning in class, always have these pre-figured out. I didn't finish this one, and I didn't have it pre-figured out. I had it started, and then just for whatever reason, because you actually never do it this way, except to learn what you're doing. You do it. You always do it once, so you say, "I'll never do that again," and then you just do it the easy way. Compute. All right. Oh no, that's not the right answer. I would not give myself something that terrible. Let's try this again. Yep, I messed up. Hold on. Oh yeah, if this is minus 4, if I move it over, this becomes 7. Hi. This is why you do not do mental math. This is 7, and if this is 7, this is indeed minus 14 plus 12. So it's being negative 2, so this becomes positive. Oops, positive 3. I have all the steps right except for that last one. That's why I butchered it. Yes.
I think it's a negative 6z equals 24.
That's what I did wrong. Thank you. All right, so do we ever do math this way? Let me ask you. The answer is no. We do it once to show you why you never do it this way. So let me just do the next page, and I think the next page is just where we make everything easy on you. Let's do actually, yeah, the next 2 pages is correct because we'll redo this again, and except we use the shorthand notation, which I don't get lost with everything. Okay. Thank you. All right, so let's do this. All right, so let's look at this for a second. Let's look at this for a second before we go on. Do I need to write x every time? No, it's always going to be x in the first column. Do I need to write y every time? No. Do I need to write z every time? No, right? Just extra information which could get you all confused, including me, right? And so what we define here is what we call an augmented matrix. So we take this, and we just say, here, given any system, I'm going to write this as a matrix, which we can use to solve simple equations, and we can see this easier, right? So we're going to do this just so we have placeholders for all this. And so here, we're just going to write this out. So here we just take the coefficients of 1, minus 2, 3, 7. And then we'll have 2. Oops, hi. I don't know where that came from. 2, no. 4, 2, minus 1, 42. 3, 2, minus 5, and 5. The dotted line's up to you. You don't have to have it. I usually put it. Here's to show another example. Here, if I have the system, it'd be 3, minus 2, 1, 2. There's no x, so you put in a 0. 2, minus 1, 1. And then there's no x, no y. And then for z, we'll put in a 5. equals 15. Oops, no equals 15. And here you can have this line. And so we call these augmented matrices. And so basically we've taken all this information here and we've just thrown away the repetition to make it easier for us, right? So we've thrown away the repetition to our repetition. So go ahead and give these two a try real quick on your papers before I give you the answer. So write these as augmented matrices. I'll come back and give you the answers. I'm going to fill up my water real quick, and then we'll go to the next one. Come here. Come on, your show. Oh. All right. You guys get answers?
Yep.
All right. So here are the answers. So go ahead and check them against yours. So make sure, what I'd be very careful about is making sure you have the zeros in the right spots. If not, you get totally wrong things. Started filling up my water. All right. So let me explain how to do it the quote unquote easy way. It's not any easier. It's just less, there's less stuff everywhere. So it's just, you get less lost. All right. Yes, we will do. Okay, we don't need to finish this. Let's go to here. All right, let me actually show you page. Let me show you the top of page 6. We'll finish here with page 5. We'll do this once. And so here, let me zoom on in. So here, once we put everything into an augmented matrix, row operation. So these operations do not change the solution system. They're actually the same before. If I switch 2 rows, it's the same thing as switching 2 equations. If I multiply 1 row by a non-zero constant, same thing as multiplying an equation by a non-zero constant. If I add a non-zero multiple from one row to another, it's the same thing as adding a non-multiple of one equation to another, right? We put zeros in for, so you wouldn't put zeros in for the z columns, no, because there isn't any z's. Yes, so sometimes some equations will not have zeros. So you'll have system of equations, so you might have 5 unknowns and 2 equations. You might have 10 equations and 2 unknowns. This method actually, I'll teach you, will actually sort it all out in the wash. So it's not possible. It won't show up as possible. And the other is matrix because they do have that variable. Yes. Hey, you. Hold on. Sorry. Anyways, and so we're going to do this again for this system. We're going to go through all the steps, but let me show you what the goal is. So let's first make the augmented matrix. So let's first write this as an augmented matrix. So I want to have 1, -1, 3, 1, 2, -2, 3, -1, 5. And then we'll have 4, 10, and 14. Okay. So what's the goal here? The goal is we're going to look on page 6. So here, we're going to put it in reduced row echelon form or row echelon form. It's not super important. what it means is a matrix in row echelon form has the first thing in a non-zero number in a row is a 1. We call that the leading entry. The leading entry is to the right of the leading entry above it, and all zeros below. And then we have this where if it has a leading entry, make everything in that column 0. We're going to use what we call Gauss-Jordan elimination algorithm. This is what all your computers use to solve it. And so basically, given the system of the equation, what we're going to try to do, can we not highlight no more? Thank you. What we're going to try to do is we're going to try to get a 1 up here. Once we get a 1 up here, it's going to be real easy to get rid of. We just multiply whatever constant's here. We can easily multiply this by a negative of whatever's here to make a 0, and a negative whatever here to make a 0. Then we're going to try to get a 1 here. And then we'll take the same thing, put a 0 here. And then we're going to try to get a 1 here. And then we'll just back substitute. And this actually prevents this back substitution. So the boxes mean whatever. And so we're going to try to actually follow the algorithm this way. We're going to have a matrix that looks like this. Actually, we're starting here. We have a matrix that looks like this right now. So our next goal is to put zeros here. And if you deviate from this, you're going to kind of ruin your work. Because if I get a 0 here first, right, for say, I get a 0 here first, but I haven't zeroed out this row, when I zero out this row, I'll probably ruin my 0 here. Just how it works. So there's a very particular method. You always follow this, and after you do it like 2 or 3 times, you have it in your head. So let's do it. Let's do this one. And I'm going to show you kind of shorthand notation. So I'm going to show you my shorthand notation. So I'm going to take a copy of this row. I'm going to take -1 of this row and add it to this row. And how I show that is I just do a little arrow, say -1 times that. I'm going to do this one kind of slow, and then I might do the other ones a little bit faster so we make sure we get done on time. So the first row hasn't changed, so I'm going to rewrite that row. The third row hasn't changed, so I'm going to rewrite that row. And what sucks about doing these, if you make an algebraic error anywhere, you have to go all the way back, and it takes forever to figure out what you did wrong. Forever, trust me. I hate writing these because I'm like, okay, where did they go wrong? And it takes me years. Now, if I take 1 minus negative of this row would be 0. 2 minus negative of this row would be 3. So 2 minus a -1 would be +1. So 1 plus 3, or 1 plus 2 is 3. -2 minus -3 would be -2 minus 3, sorry, it gives me -5. And then here I'll have 10 minus 4, which will give me 6. Is everyone okay with the first step? Any questions how I went? I'm just taking negative of this row, adding it to this row. No? Okay, I'm going to keep moving forward so we can finish this page by the end of class. All right, so here, I'm going to just take -3 of this row and add it to this row. Why? Because that will cancel out this and make this a 0, which is our goal, is to get zeros and zeros. That's our first goal. So it'll be 1 minus 3, 0, 4, 0, 3, minus 5, 6. Often I'll do both of these at once on the same line, but for when I'm first teaching it, I shouldn't. So this is a 0 by design. So 3 minus 3 is 0. 1 plus 3 would be 2. 5 minus 9 would be -4. And then 14 minus 12 would be 2. Okay, so that's where we're at. So let's look at where we're at in our algorithm. So where are we at in our algorithm? We have achieved, so we went from a matrix, we put a 1 up top, and now we have 2 zeros here. So our next goal is to put a 1 here. That's our next goal. So I could divide this, I could divide row 2 by 3, and I'd achieve that goal, but then I'd have a fraction here. And who loves fractions? Nobody, right? But notice if I divide this row by 2, it divides nicely by 2. So what I'm going to do is I'm going to switch these 2 rows. And when my symbol for that is just an arrow here and an arrow here. And the reason I'm switching those 2 is it'll make my life easier. That's 1, -3, 4, 0, 2, minus 4, 2, 0, 3, minus 5, 6. Oops, that's a funny looking 6.
I think you missed a negative on top.
You're right. Thank you. Because if I didn't copy that out, I would have carried on.
Yeah.
Forever. Thank you. All right. So now that I've done this, I'm going to divide this row by 2, and I just draw a little division by 2. That's how I write it. So when we do that, I'm going to get the following. So I'll have 1. Oops, my computer's getting a little chunky. 1 minus 1, 3, 4. Didn't do anything to that row. Didn't do anything to the bottom row, so I'll just copy that one down as well. And this one I divided by 2, so it should be 1 minus 2, 1. All right, so if we look at our little algorithm, where are we at? So now we've achieved this. Our next goal is to put a 0 here. That's our next goal. So to do that, we're going to just take minus 3 of this one to this one. So we have 1, negative 1, 3, 4, 0. Oops. 0, 1, minus 2, 1. This 0. This is 0 by design. The next one should give us negative 5 plus 6 will give me positive 1. And then 6 minus 3 will give me 3. Okay. Let's look at our algorithm again. We're almost there. Let's look at this algorithm. So we have a 1 here. Or we actually achieved, we not only got this, but we got this as well. So the next thing we want to do is 0 out here. So we're going to 0 up. I'm going to do that in one step. And so here, in order to 0 this up, I'm going to take minus 2 here, and then I'm going to take, or no, positive 2 here, and then minus 3 here. So the first row would be 1, negative 1, and then if I'm adding negative 3 of this row to this row, it gives me 0. Negative 3 to this row will give me minus 9, so minus 5. This one gives me 1, 1. And then if I add 2 of this row to this row, it gives me a 0. And then this one to this one should give me 7. Yes. 0, up, 0, 1, 3. And then the very last thing I need to do is 0 out this one. It's the last thing in our algorithm. And so we're just going to add 1 of this row to this row. Gives us our final matrix here, which is 1, 0, 0, 2, 0, 1, 0, 7, 0, 0, 1, 3. Now, if I was going to retranslate this into what this means, that means x plus 0y plus 0z equals to 2. Here I have 0x plus y plus 0z equals to 7. And then if I have 0, 0 plus z equals to 3. And so here you can just literally read off the answer. And that is the answer, right? And you can check it real quick. Here you can check it. I do that for you right here. Here I've done it for you. So here I've checked it. And you can check each one and every one of the equations to make sure it's right. So that's what the goal is. Our goal is to eventually just do it this way. So here we go. Let's talk about determinants. Whoop, whoop, whoop. All right, so determinants. Determinants is a way for math to kind of boil down these huge matrices into a single number, right? So if I give you like this huge matrix, it's like, well, what's that roughly? Well, a determinant. Well, is that roughly what that matrix is? No, not really, but it is a number that has lots of uses, right? So this has tons and tons of useful properties. And so if I was going to boil down a 1-by-1 matrix to a single number, what number should I pick? The number in it, right? That's what I would do. I'd pick the exact number in it, right? And then for a 2-by-2 matrix, for reasons we will not get into in this class because we're not that big of into the philosophy, we're going to just take we're going to multiply the diagonals, which we call to be the trace, right? And then we're going to minus this one. So here it's going to be the product. We're going to take this, multiply down, and then minus this multiplied across, right? So this is the number we're going to call to be our determinant. So in order to do this, let's just roughly go through this. All right, so here in order to do this, this will equal 3 times 6 minus the quantity of minus 1 times 4. And if I crunch through that, I get 22. Here, this will be 1 times 4, so 1 times 4. And we determine the determinant by having these nice straight lines. So 1 times 4 minus 2 times 3. And that gives us minus 2. And this gives us 1 times 4. So this is equal to 1 times 4. And this equals to minus 2 times 2. Well, this is 4 minus 4, so it gives us 0. So this gives us 0. Notice if we have a 0, so if the determinant is 0, bad things happen, right? I don't know if you guys ever taken a linear algebra class that says this matrix is a non-matrix is non-singular means, and then it's a whole host of things, right? Right? There's a whole host of things it means. And one of the things it means is, as long as this is not 0, it should have a nice answer. But this is 0. And so the matrix, at least in a system of equation sense, doesn't really have a nice answer. And if I reduce row echelon this one, right? If I reduce row echelon form this matrix, I'm going to get 1, 2. Well, this would just be 0, 0, right? And so if this was the beginning of a system, we say, well, this system doesn't have a unique answer, right? And so having determinant equal to 0 is bad, right? A lot of bad things happen, right? I'm a numericist, right? And if your matrix equals some of your numerical properties for solving some of them, not all of them, but I can't think of any example against it, but most of them, if you have a determinant equal to 0 in your matrix and you're trying to solve something, the numerical methods just slow down. They just do it, just because it doesn't work as well. Because you run into loads of problems. So that's kind of why we do it. We'll get into other reasons why we do it later. So for determinant for 3 by 3, so if we're going to do a 3 by 3, we break it into pieces, right? And we call this the expansion across the top row. This is what they teach you if you watch. This is what they taught you in any linear algebra class. So you can go across the top row. So basically what it means go across the top row is that you're going to take this, and I'm going to, hold on, make sure I'm on the right layer, which I'm not, because I'm going to make marks and erase it a lot for 2 seconds, just so I can really explain what's going on. If I'm going to expand across the top row. So what I usually do is I usually put a little arrow right there. If I expand across the top row, I'm going to take the first element, and I'm going to cross off everything else, right? So I'm going to cross everything else. So it'll be A1 times the determinant of what's left. A22, A33, A32, A33, right? So it's just what's left. Then I'm going to take the second element, and then I'm going to cross off everything in that row and in that column. And then here I'll get A12, ignore the sign for a second. And then it'll be what's left here. So it'll be A21, A23, A31, A32. And then the last one will be, I'll take this, and I'm going to cross off that row and that column, and then find the determinant of what's this. And so even if this was like an n by n, you could slowly whittle it down to a bunch of 2 by 2s, right? It just takes you more time. Okay, so we call this expanding across the top column. And so basically, once you cross that off, you get a matrix which is 1 by 1 smaller, right? And you can only take determinants of square matrices at this time. Now it's just like, well, can you take them at other times? Well, you get pseudo things, right? That's what we call them. So it's formed by removing that row and that column. Now you can do this across any row and any column, and we'll actually show you doing it across different rows and different columns, right? But you're going to need to memorize this. Do you need to memorize it? Not really. Just remember it goes in a checkerboard pattern. It'd be plus, minus, plus, right? So here it's plus, minus, plus. If I went across the second row, it'd be minus, plus, minus. Just the sign before you do everything. Okay, so that's how we do that for a 3 by 3. So we've talked about it. Let's actually do it. We're actually going to do this. I'm going to explain it to you by doing this many different times, right? So we're going to do this multiple times. So you get very used to doing this in any order, because some of them make a lot more sense than others, right? So here, I'm going to do this by expanding across the top row. So I'm going to go across this top row. So the determinant of this is going to be equal to 1 times the determinant, and then here I'm going to cross this off and put this off. So if I did that, I'm left with, if I did that, oh, I have an eraser, 4 minus 1 minus 2, 0. Okay, but remember my signs to be plus, minus, and plus. Okay, so here I'm going to hit minus because that's my next one. And now I'm doing 5. So it would be 5. And then I cross off that row in that column. So I'll have the determinant of 2, negative 1, 0, 0. All right, then it's plus. So it would be plus. And here we'll have 0. And so we'll cross everything off. That's 0 times 2 times 4 times 0 times negative 2. All right, so let's calculate this real quick. This determinant is positive 2, or no, hold on. This determinant is 4. I'm going to just write it out. 4 times 0 minus negative 2 times negative 1. So it becomes, this is positive, but then it becomes negative again. So this is minus 2. So this is all minus 2. This is 5 times 2 times 0, 1 times 0. So this is plus 0. And this is 0 times, we don't need to calculate that. That's a 0. So this gives me minus 2, right? Minus 2 is the determinant of this matrix, right? Let's do it across the second row. So I can also do the same thing across the second row. So now, if I'm doing it across the second row, I need to memorize. So here, if this was a plus, I walk down, this is a minus, and then it'd be plus, minus, right? So every time you move, just switch the sign, okay? So here, if I'm going across the second row, it'd be minus 2, and then I'm going to cross off this and this, and then I'll get the matrix of 5, 0, minus 2, 0. Then it'd be plus, notice the plus here. And here I'm going to cross this off and this off. And so it'll be plus 4 times 1, 0, 0, 0. And then here, go ahead and get rid of this. And then it'll be minus a negative 1 times, cross these off, and I'll have 1, 5, 0, minus 2. Is there any questions on how I built this whatsoever? Let's go ahead and stop if you, I've done it enough times that if you were confused the first 1 or 2 times, you might have seen how to do it by this time. If not, if you're confused, let me know now. All right, any questions on that? No. All right, so let's find the determinant of this. Oh, a second. So is the cross product or even dot product basically works? Since then, so how is the cross product or even the dot product work? Basically work like since they have matrix values. So the cross product and the dot product are things defined for vectors, and that only works. But determinants will only work if, unless it's a 1-by-1 vector. You cannot do this for vectors because it has to be square. These have to be square. You can only find determinant of square things. They have to be nice little boxes. Okay. All right. So let's crunch through this. This determinant is 0, so this is 0. This determinant is 0, so this is 0. 1 times 0, 0, 0, 0. 5 times 0, 0, minus 0, 0. This is the only non-zero one. So we have minus a minus 1 times, well, here we'll have minus 2. Minus nothing, so 0. So this equals minus 2. All right. Now, is this what I would do? No. I would do one of the following. I would do definitely one of the following. I would either do the bottom row or the third column. Why? A lot of it zeroes out, right? 0, 0. So the only thing I need to worry about here is this, right? What's the sign on this? Well, it's negative, right? We already determined the sign. So if we're doing across the third column, it'll be minus, minus 1. Let me zoom out so I can see everything. So it'll be minus 1 times 1, 5, 0, minus 2. And then the first one is 0 plus 0. And I know what this is. We just calculated it. That's minus 2. Or we could go across the third row. So this is plus, minus, plus, and so this would be plus, minus, plus. So it would be 0 minus a minus 2 of the matrix. Hold on, this would be 1, 1, 4, 5, 1, 1, negative 1. Hold on, 1, 0. Be very careful here. 2, negative 1. Let me show you what I'm doing. So here, if I'm going across this row, not this up here, I want, so the only one that's not 0 is this one, which would be negative, right? Because this was positive. So I cross off this. So I have 1 and 0, 1 and 0, 2 and negative 1, 2 and negative 1, plus 0, because the other one's 0. So I really don't care what the determinant is. I calculate this, I get negative 1 and a positive 2. So this all equals minus 2. And notice these all equal the same, negative 2, negative 2, negative 2, negative 2. So it makes sense to choose the column with the most zeros in it. Really it does, just so you have to do at least amount of work. Okay.
Excuse me?
Uh-huh.
Can you please explain how D equals -2? For some reason, I'm getting +2. And I don't know what I'm doing wrong.
Because I probably missed the negative sign.
It's minus 1.
Oh, so it's minus 1. Thank you. Because here, hold on, let me do this one very clearly. I'm going this way, right? This is plus, this is minus, this is plus, this is minus. So here it's minus 1. So it'll be minus the -1. And then when I cross these two off, I get -2. And so here this gives me -2. So minus -1 gives me +1 times -2. Yeah, sorry, I didn't write down the negative sign. Too busy explaining what I'm doing, not paying attention to what I'm actually doing. So.
Excuse me, how would the order go if like we're going across the columns, like for the determinants, the 2x2?
For a 2x2?
Yeah, like for example for D,
Oh,
you went like 1, 5, 0, -2, but how would it go for the zeros?
so let's go, let me just show you, let's just go this way. Let's just go down column 2, because that's a lot of non-zero things, right? So plus, minus, plus, right? So this would be plus and then minus. So it'd be -5. And then here, I'm going to cross off this and cross off this. And so I'll get 1, 0, 0, 0. So 1, 0, 0, 0. Then it'll be plus the 4. And if I add the 4, oops, no, 5, hold on. I did the wrong thing for 5. 5 should be, if I go down the second column, 5 should be negative. This should be 2, -1, 0, 0, 2, -1, 0, 0. Then if I go down to the 4, that is the plus. Cross off that, so I get 1, 0, 0, 0, 1, 0, 0, 0. And so what I'm doing here is I'm crossing off the column and the row in which the entry appears. So this would be minus a -2 times 1, 0, 2, -1. Okay, does that make sense how we got that?
Yes, thank you.
Okay. All right, so let's finish our last 3 pages.
Wait, can you show the 3x3 matrix rules again real quick? I wanted to see something. Oh, okay. No, I got it. Okay, I got it. It was the T thing that was like, okay, I get it now.
Okay.
Okay. All right. Thank you.
All right, so let's do this. So now we know how to do that. We can do an n by n, right? So we can do it across the top row. I can do it by a row of your choice. So let's just do the top row real quick. So here, remember the pattern is plus, minus, right? So if I do the top row, I'm only going to have 2 sets of matrices. So I'm going to have 1, and I'm going to cross off this. So we're going to have 1 times the determinant of 0, 1, 0, 1, 0, 1, 4, 0, 0, plus Oh, no. So it is plus, so it'll be minus minus a 2. Hopefully that won't. No, let me write it as minus minus 2, even though I'll forget. I'm going to cross off this row in this column, and we'll have 2, 1, 0, 3, 0, 1, 0, 0, 0. I'll give you a hint. If any column has a 0 row or a 0 column, the determinant of that matrix is 0. Okay, does that make sense? Because you just expand across this column at 0, 0, 0, 0, right? It doesn't matter what size it is. And then here we have a 0, so plus 0, and here we have a 0 plus 0. Okay, and I know that this is 0 because this, I have a 0 row, right? And so if I expand across this row, it would be 0 times something, 0 times something, 0 times something. So I know all of this is 0. So I'm just left with this, right? 1 times whatever this is. So if I was going to expand across something, what would I do? Well, the bottom row, right? So I'll have 1. And so this is plus, negative plus. And so this would be 1 times the quantity of 4 times, if I cross this off and cross this off, 1, 0, 0, 1. And then here it'd be 0 and 0 for the other two. And I'll get 4. Okay. All right, so now go ahead and give it a try with any of them. So go ahead and expand across any row or any column you like and give it a try. I'll give you a hint.
Professor, I have a question. For letter A on your first one, you put -1 on the second row instead of just +1.
In this one?
No, for example 3, letter A, yeah, for the second row, you put -1, 0, 1. Isn't it supposed to be 1, 0, 1?
Oh, hold on. In this?
Yes, in that one, in the second row.
Oh, you're right. This should be a positive. I don't know where I got the negative from. I let it down. Okay, thank you. All right, so go ahead and give it any try of your choice. And as you do that, I am going to open up the last 2 pages. All right, so go ahead and export it. I guess I'm going to save this one. Let me save this one. It's fine. Goodbye. Don't say goodbye. See this? Don't say goodbye. Let's open up these last 2 pages, and then we have 15 minutes to complete them, which should be plenty of time. Hopefully. Who knows? I could get horribly behind. Great page shuffle. All right. So there's many choices you could have done. I'm just going to give you one of them. I would have done probably the 4th column. Just what I would have done. So this is negative, positive, negative, positive. And so here I'll have -1. If I cross that off, I'm going to get the following. So this is 0, 0, 0. So it just ends up being just 1, -2, 0, 2, 0, 1, 0, 4, 0. And then at this point, I would expand across the last one again. And so this would be -1 times, so this would be plus, minus, plus, minus, so it'd be minus the 4. And then here, if I cross this off, I'm going to get 1, 0, 2, 1. And this just equals, well, this is 1 and 0. So this is the determinant here is 1. So it just equals 4. Now to type it into any computer algebra system, you're just going to type in DET and then you can put in your matrix and it pumps out, it'll pump out your determinant for you. Okay. All right, so let's find out what the determinant of this is. This is a 5 by 5. Now, can anyone guess what the determinant is without me doing a lot of math? 0? No. There's no 0 row or column. But a good guess.
1.
1's a nice guess too. I love all the guesses. So it's good, but let me just kind of crunch through it real quick with you. I'm going to expand across the bottom row, right? So it's 0, 0, 0, 0, and then -6, right? But notice here that the diagonals are always positive, right? Because as I wander, these will always be positive. So all the diagonals will be positive. So I'll have -6 times this matrix. Well, what do I choose then? Well, the bottom row, right? And so it'll be -2 times this matrix, right? Well, I'll just choose the bottom row again. So it'll be 1 times this matrix. Well, I'll just choose the bottom row again, right? Which gives me 2 times this matrix, which of course is 3, right? So it's just, all I'm going to do in this case is I'm going to just multiply that across and I get 72. So if a matrix looks like is either what we call upper triangular, means it has entries up here and zeros down below, or lower triangular, where it has zeros up here and entries down below. And what I mean by that, to be very clear about it, for a 3 by 3, it'd be star, 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 and then 0, 0, 0. So this is this right here. Let me kind of clean it up, seeing how I drew all over it. This is upper triangle, right? As long as everything below the diagonal is 0, we call that upper triangle. If everything above the diagonal is 0, so pretend if all these numbers right here were 0, right? We call that lower triangle, right? Where all this stuff is in lower triangle. If it's either upper or lower triangle, all you have to do is just multiply across the diagonal and you get your determinant. Okay, now someone have the answer. So, well, let's do math. Well, sometimes I can just do row operations, and what row operations do to it matters. And so let's kind of, we're going to show all the following statements are true for row operations. So I'm going to perform row operations on this, and then we're going to show that all of these do exactly what they pretend to do, and then we'll solve one that way. Okay. So let A be a square matrix. Why? Because then we can take a determinant, right? And A is if we multiply one row by K to produce B, then the determinant of B is K times the determinant of A. So let's start with the first one. We'll just call this one 1, right? We'll just do this one. So and also another way of saying it, the determinant of A is equal to 1 over K times the determinant of B. And the reason I'm going to write this out as well is that if we want to know what A is, and I start doing all these operations, we got to do the inverse of what is shown here, right? Well, this is the only inverse that matters, right? Because this determinant of A is equal to determinant of B, that's fine. Here, the determinant of A is also equal to minus the determinant of B. And so here, it's nice to have these. So let's just do this. I'm going to take the first row and multiply it by K. So here, let's find the determinant of KA, KB, C, and D. Okay, so in order to do this, we're going to multiply KAB with KAD minus KBC. Well, what is that? Well, that's K times AD minus BC. Well, what's AB minus BC? Well, that's the determinant of A. Okay. Oh, sorry, I forgot my little K. So K times the determinant of A. So this is where this one comes out. If I multiply one row by K, what I actually end up doing is this. We're gonna show, we're not proving because I'm only using a 2 by 2. It works for 3 by 3s and 4 by 4s, right? All right, so that's why this one pops out. Now we're going to interchange 2 rows. If I switch 2 rows, I get negative of the determinant. So here we're going to put CD up top and AB down below. And we're going to find out what the determinant is. So here I'll have C times B minus A times D, which is equal to minus of A times D minus C times B, which is equal to minus the determinant of A. So here we see if we swap the row, we're actually going to introduce a negative into it. Now, the last one's actually quite interesting. If I add a multiple of one row to another, I don't change my determinant at all. And so this is actually the most useful one because you can do this as much as you like and never change your determinant. So let's do that. So this is 2. Oh, hold on, let me mark this. So let's say this is 2. This will be 3. So let's do that. So let's have 3. And we'll go ahead and add, in this case, we move stuff up top. So let's do stuff down below. So here we'll have K, A, and B. And then here we're going to have C plus AK and D plus BK. So I'm adding K times of this row to this row. That's something we did a lot when we were solving, putting stuff in row echelon form, right? We did this a lot, right? All right, so if I do that, I'll have A times B plus BK minus B times C plus AK, right? Let's multiply that out. Here I get AB plus B, or ABK minus BC minus, make sure to carry any negative, BAK. Well, these are the same, so I cross that off. And so what am I left with? AB minus BC, which is just equal to the determinant of A. So this one is the most useful. All right, so we have all these fun rules, so we'll go ahead and leave them up for a second, and then we'll do our last page for the day. No, I didn't finish it. Of course. What would be the fun in that? All right, so let's do the last page. If you need this page again, I can open it up at the end of class. All right, so let's do the last page so we can get out in time. So we're going to use row operation to find these determinants. Is this nice to find a determinant of? No, just nothing clean to get rid of. However, notice if we just do a very simple row operation. So here, I'm going to take this matrix before we're going to find the determinant of it. But here, I'm going to go ahead and do minus. I'm going to add 2 of this row to this row. And I'm going to add 1 of the top row to the bottom row, right? And if I do that, and we'll go ahead and switch over to a determinant. Whoops, I'm on the wrong layer. That's my number one mistake in teaching. I have a layer where I can erase freely, and I have a layer if I erase it, things go bad. All right, so let's do that. So the first row is the exact same. 2. This, if I add 2 of this row to this row, I'm going to get 0, 0, and 5. So 0, 0, 5. And then here I'll get 0, 3, and then 2. So this is 0, 3, 2. So these are just doing the row operations. You're doing this before. Make that look a little more like a 2. Okay, so now I've done 2 row operations. How does that change the determinant of this matrix? Not at all, right? Because I'm adding 1 row to another. I've done nothing to this. So the determinant of this matrix is equal to the determinant of this matrix, which is equal, I'm going to go ahead and switch these 2.
Excuse me?
Yeah, go on.
I think it's -5.
Yes, you're correct. Thank you. Thank you. So here, when I switch these 2, I'm going to negate, because I'm switching rows because of this, right? If I switch rows and take the minus, so I'm going to minus that. But why am I going to do that? Do I know how to find this? Yeah, it's just multiply the diagonals. And so here it's negative, oops, times 1 times 3 times -5. And what do we have here? We have this equal to 15. All right. So let's look at this. All right, so here, let's pretend we have this matrix right here. Given this matrix, we want to produce something that's easier to find the determinant of. Now, if I went down one of these rows, the best I could do is still find two 3x3s, right? That'd be the best I could do, right? If I went down this row or this row, it's the best I could still have to find at least two 3x3 matrices. But in this case, we're gonna just do some row operations. And the first row operation, we're gonna divide by 2. Now, dividing by 2 is technically multiplying by a half, right? Technically, that's what I'm doing, multiplying by half. And so here, if I want to keep I want to know what determinant of A is, so I'm going to have to divide by 1 over a half. Well, 1 over a half is 2, right? So this is equal to 2. And then here, we're just going to half out this row. So it'd be 1 minus 4, 3, 4. Then here we'll have 3. Oh yeah, this is just the same. 3 minus 5, 10, minus 3, 0, 1, minus 2, 1, negative 4, 0, 6. Okay. All right. Then the next step, I'll show you the next step. And since we're almost out of time, I'll just show you how to type this in. No, we'll finish this. I guess we can finish this real quick. All right, so this is what we're going to do for each of these rows. So I'm going to multiply this one by minus 3 of this row. And I'm going to do 3 to this row and this one. What does that do to my determinant? Nothing, right? It does absolutely nothing. I guess I should do what I've been doing and just go down from here. So this would be 1 minus 4, 3, 4, 0, 3, minus 4, minus 2, 0, minus 12, 10, 10, and 0, 0, minus 3, and 2. And here we have 3 by 2 here. Now, and we'll go from here. All right, so the next thing we want to do from here is notice we don't necessarily have to have a 1. So we're just going to go ahead and get rid of this row by multiplying 4 times this row to this row, which will zero this out, because all we need is upper triangular, and that actually just works out fine there. So let's go ahead and do that. So this is 1 minus 4, 3, 4, 0, 3, minus 4, minus 2, 0. Oops, now I've done that. You'll get 0, minus 6, 2, 0, 0, minus 3, 2. And then to finish this off, we'll just multiply half of this row to this row. And then we get the following, which is, oops, I forgot my 2. Make sure to carry your 2 from when we multiply by half. So we'll have 2 times 1 minus 4, 3, 4, 0, 3, minus 4, minus 2, 0, 0, minus 6, 2, and half of this added to that would be 0, 0, 0 by design. And then here we're left with half of minus a half of this, because I want to make this positive. Hold on. So minus half of this will make this positive 3. Add that to that would be 0. So make this negative 1. Add that to that would be 1. And then here we can just go ahead and crunch this out. So it would be 2 times the diagonal. So it would be 1 times 3 times a minus 6 times 1. Add that all up, I get minus 36. And at any point here, we could have stopped and just calculated the determinant directly. But usually if you're on this train, it's easy enough to get here unless you get a fraction. At some point, you're like, okay, I'll just stop. Okay, so that's how you finish this problem. And that's the end of these notes.